Hello everyone. In this lecture, we'll be learning about how we can use sequential circuit in Verilog. So, for the first example, in explaining sequential circuits, we'll be using an up counter. So, uh, let us create a new project. We write up. Let us name it up count. And next, finish. Okay. And let us open a Verilog HDL file. Now, what is up counter? Let us suppose this is an up counter. We have to, since we are using HDL, hardware description language, we have to think in terms of hardware. So what is up counter? Up counter will have a clock signal. As long as we'll get a positive edge of the clock, the count will increase. Suppose this is a 4-bit up counter, so we have the output as 4 bits. Q0 to Q3. We have 4 bits output, and as soon as the clock signal is present, the output will change. That is, initially if Q is 0, if clock signal is present, Q will be 1, next it will be 2, next it will be 3, and so on. Now what we can do, we can provide another input pin as reset. That is, when reset is asserted, that is when reset is equal to 1, what happens is it makes all the Q's is equal to 0. So as soon as we assert reset, what happens is output becomes automatically 0. Another thing we can do is we can use our L0 to L3. We can use some load operations using our input load. As soon as we apply load, what happens is it sets Q is equal to L. L0 to L3. Whatever the value is L, it assigns that value to Q. So what happens is the circuit works is as soon as the clock is in the positive edge, the Q is increased by 1. If reset is asserted, and then Q becomes 0. If load is asserted, that is, if reset is 1, then Q becomes 0. Else, if load is 1, then Q becomes L. Else, Q becomes Q plus 1. But these all things will happen at the positive edge of clock, whenever the clock finds its positive edge. So we are writing that piece of code. Uh, let us write module up count. Its output is Q. Input are clock, reset, load, L. Of the inputs, L is 4 bits, as it is a 4-bit counter. So we get L, we define L like this, and we define uh, clock and reset and load a single bit. And output would obviously be 4-bit. That is, we define as 3:0 Q, since it is a 4-bit counter. Now again, always at the rate, always block. One thing is to be noted that since we are calling upon the always block, we make the output register type. One thing is to be noted that all the operations that are being done will happen at the positive edge of the clock. To define it, we can write pos edge, pos edge clock. We can also write it as neg edge. If we write it as neg edge, it happens at the negative edge of the clock. So since our problem is defined for the positive edge, we write always at the rate positive edge of clock. At positive edge of clock, what happens if RST equal to, if the value of reset is 1, then what happens? Q is equal to 0, Q is set to 0, if, let me see, else if load equal to 1, if load is 1, it sets Q is equal to L. Else it sets Q is equal to Q plus 1. The code is as simple, really simple code. We save it and we try to compile it and see if it works. As we can see, thankfully there is no error. Now we open a vector waveform file. We insert node or bus. Now we suppose we set L as suppose we set L as 5. So as soon as the load is 1, load is asserted, Q will be equal to 5. Now we put a completely random clock. We put a random clock over here. At the initial stage, we have to reset a bit because at the initial stage there is no value of Q available. So we assert reset here. And for the sake of understanding how the thing works, what we do, at certain stage here we assert our load. So we select this portion and we make it high. So load is asserted here. Again at certain stage here, for just for the understanding, we assert a reset and see if everything works correctly. We save it. We change the settings to functional, and what we do is we generate functional simulation netlist. It was successful and we run the code. Now let us see what happened. When the reset is asserted, what happens is Q is equal to output is equal to 0. When the reset is not asserted, output was originally 0, and when at the positive edge of the clock, output became 1. At the next positive edge, output became 2. At next positive edge, output became 3. That is, output kept on increasing one by one. It became 4, 5, 6. Then 4, 5, 6. Then what happened? It found load. At this positive edge, what it saw is it saw that load is activated. Since load is activated, it loaded 5 into the output. So the output became 5 again. And since load became deactivated next, so it kept on increasing like 6, 7, 8, 9. Then again at this positive edge, it found that reset is activated. After reset is being activated, it again makes the output as 0, and it keeps on increasing from then on as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 0. It is to be noted that we, throughout the entire code, we did not make any point, or we did not make any condition which states that the output will be equal to output will start from 0 as soon as the output becomes 15. That is, after 15 the output will start from 0. But why did that happen? That happened because we have defined the output as 4-bit. This is a 4-bit counter. So in order to write 15, the value of Q becomes 1, 1, 1, 1. If you add 1 to it, it becomes 1, 0, 0, 0, 0. And the Q assumes the value of the 4 least significant digits. That 1 at the most significant bit is neglected, and from 15 it again becomes 0, 0, 0, 0. If it was 4 to 0, that is 5-bit adder, then we would have gotten the output till 31. Then again we would have gotten 0. So this is how a simple up counter is working. Now let us modify the up counter a little bit. Let us create a new project. So we get file, new project wizard. We name it, suppose we name it T2. Finish. We write a module. My mistake. We write a module. We Verilog HFN module E2. Now let us define the problem statement. The problem statement is as such. Now we are making a simple counter. We are making a counter which counts from 2 to 10. That is, what happens is it will have a clock, it will have a reset, where the counter will start counting from 2 and as soon as it reaches 10, in the next count it starts from 2. And if reset is applied, reset also will make it start from 2. This is how the counter is supposed to work. That is, it is 2 to 10 counter. So our output is Q and our input are clock and reset. So we define input as clock. Our problem statement did not tell us to use a load command or load any value, so we are not using it. We are not increasing the complications. Output, since output is 4-bit, 320, we have Q as output. Now again, always at the rate pos edge clock, always at the positive edge of clock, if RST is equal to 1, if reset is equal to 1, we will make Q is equal to 2, since it is 2 to 10 counter. Else if what happens? Q is equal to 11. If Q becomes equal to 11, if Q becomes equal to 10, after 10 what we do, we make Q is equal to 2. Else Q is equal to Q plus 1. So the logic is, if reset is exerted, we get Q is equal to 2. If the Q becomes 10, in the next clock cycle, the Q will become 2 because it is 2 to 10 counter, and in all the other cases, the Q will be increasing like it has been doing in module. So we save it and we simulate it, or we compile it, see if there is an error. Okay, there are errors. Maybe there is a mistake that we have done. What we have done, we have forgotten to include as wedge. That's why it's showing the error. Since always block is used, the output will be register type. This time, hopefully there is no more error. Okay, there is no error. Now let us simulate it. This vector waveform file. Now what we do is we insert an arbitrary clock, and for the first cycle we assert the reset. We apply the reset, we save it, we go to projects, assignment settings, we make it a functional simulation, and processing, we generate the functional simulation netlist. Okay, now let us run net. Let us see the count starts from 2. From the positive edge of circle, it found reset is equal to 1, so it set the count to 2. It goes 3, 4, 5, 6, 7, 8, 9, 10. After 10, it again comes back to 2. So it again goes 2, 3, 4, 5, 6, 7, 8, 9, 10. After 10, again it comes back to 2. So it is a basic 2 to 10 counter. Now, another thing that I want to show you in this lecture is how to make a ring counter. So what does ring counter do? Ring counter works in this way. This is a ring counter. Say it is a 4-bit ring counter. So we have these 4 bits here. So these are outputs, and these are the load bits. These will be loaded as soon as load is equal to 1. This is load input. As soon as load is equal to 1, this cell will be loaded. We have clock. We have actually we do not need load. As soon as we exert reset, this L will be loaded to the output. Now what will happen is, how the ring counter works. Suppose at beginning the value of L is 1011, that has been loaded to the output because we have asserted the reset at the beginning. Then what happens is, this digit goes here, this digit goes here, this digit goes here and this goes here. So at the next clock cycle, we'll get 1101. Again, at the next clock cycle, this goes here, is here. So we'll get 1110. In the next clock cycle, we'll get 0111. Similarly, these cycle will continue. So this is our ring counter. So in order to make a ring counter, we open a new project. We name it ring. You can name it anything, but I decided to name it ring. And Verilog HDL file, module, ring. The inputs, the output is Q, and the inputs are clock, reset, L. Then what we do is we define inputs, clock, reset. Since it's a 4-bit ring counter, we define input L, and we define output, again 4-bit, Q. Again, always at the rate positive edge of clock. What it will do is, if reset is exerted, then what it will do? It will load Q is equal to L. Else, if reset is not exerted, then what will happen? Okay, let us look at it. It will make, okay, so this is our Q at this moment. So this is Q0, Q1, Q2, Q3. So what will happen? It will make Q3 is equal to Q0, Q2 is equal to Q3, Q1 is equal to Q2, and Q0 is equal to Q1. Now we can write as Q3 is equal to Q0. We copy it 3 times. Q3 is equal to Q0, Q2 is equal to Q3, Q1 is equal to Q2, and Q0 is equal to Q1. And now we see that under the else there are 4 statements. In general, in programming language, in Python, maybe we use a tab to define. I don't actually remember. In case of C, we use second brackets to define a para or what is under this L. But in case of this programming language, that is Verilog, we use the statement begin. Once we use the statement begin, that means that this else begins here, and we put end here. That means this else will begin here, and it will end here. So if we want to write multiple statements within else, what happens? What we can do is we can use begin and end, and at last we put end module. Now there is a problem with the code. The code is supposed to work, but it will not work. Why will it not work? Because by using the always function, what we have done, we have made it sequential. That is, firstly line number 9 will be operational, then line number 10, then 11, then 12. Suppose the input is 1011. After line 9, what will happen? Q3 will be equal to Q0. Now here Q0 is 1, Q3 is 1, so Q3 will be equal to 1. Now in the next line, Q2 will be equal to Q3. So Q2 will also be 1. In the next line, Q1 will be equal to Q2. So Q1 will also be 1. In the next line, Q0 will be equal to Q1. Q0 will be 1. That is, if it goes from one line to another line, at first the value of Q3 has been established as Q0, and this value of Q3 gets propagated to Q2, which in turn gets propagated to Q1, which in turn gets propagated to Q0. If this is done in this way, the output is not desired. So in this code snippet, or in this part of the code, what we want is We want all the 4 lines to be executed at the same time. We want all the 4 lines to be executed at the same time. So in order to do that, we use a statement called non-blocking statement. This equal sign over here is a blocking statement. As soon as there is an equal sign, it will indicate that this line will be executed first, then this, then this. That is, it will be indicated one by one. So we have to use a non-blocking statement in order to solve this problem. So the non-blocking statement is we place a greater than sign before the equal sign. This becomes, mind it, this is not less than, this is not greater than equal to. This is non-blocking statement. This indicates the value of Q0 will be stored into Q3. Q0, this is Q0, consider this as an arrow, is going inside Q3. Q3 is going inside Q2. And since we have used this non-blocking statement, all these 4 lines will be occurring simultaneously. I've already told you, I'll show you how to make this happen, how to, at certain cases you will be requiring to use all these simultaneously. And how you'll do that? You'll be doing that using these non-blocking statements. When we use non-blocking statement, all of the lines, all the 4 lines will be acting simultaneously, and this will give desirable output. Now let us check whether what happens when we use blocking statement. We have used blocking statement, we save it. If we compile it, let us compile it, there is an error. See, the error will be Q on the left hand side of the assignment. The error is we haven't put output range here. So we compile it again. See, there is no error in the code. That is, this code is syntactically correct. The grammar of this code is correct. There is nothing wrong with the grammar of it. There is nothing wrong with the expressions involved in it. But what happens is we are analyzing vector waveform files. We insert the node or bus. Okay. Now what we do is we load L as, since we are loading it in binary, we select radix binary here and we load as 1. Let us see here. We have set 1011 as example. So we set it 1011. And it's better if we watch the output in binary as well. So we right click it, go to the properties and select from ASCII to binary. Okay. So we place an arbitrary clock, and the first cycle of the clock is reset, exerted at reset. We save it. After we save it, like the usual, we change the setting. We use functional simulation netlist and we generate function. Okay, so now we run it. Let's see what happens. So the output, see what I've told you earlier. Since we have used blocking statement, what happens is output becomes 1111 and it stays 1111 as I had explained earlier. Now what we can do is we can use non-blocking statement, that is use a greater than sign here. And we save it, we compile it. There is no error. We generate functional netlist again. There is no error. We run. Now see, 1011, 1101, 1110, 0111, 1011. So this is working as we encounter. So this is the importance of blocking and non-blocking statements. Now, since you have understood that blocking and non-blocking statement, these are 4 lines of code and I want to optimize this code. If you are interested in competitive programming, then we have already seen what you always want to do is always want to decrease the number of statements and processing time of the code. So I can replace these 4 lines by a single line. How I can do that? Q 3 colon 0, sorry, is equal to, what happens is, see, what happens is, originally it was Q3, Q2, Q1, Q0. So what happens is, this comes here. So it becomes Q0, Q3, Q2, Q1. So we can write here Q3 colon 0 in form of third brackets in form of array. We can write first element is Q0, second element is Q3, third element is Q2, fourth element is Q1. So if we write it like this, okay, I'm sorry, there was an error. This would be actually second bracket. If we write it like this and we compile it, it works. And we what we do is we generate functional netlist again, successful, and we run, successful. So the code works again. See, 1011, 1101, 1110, 0111. So it works as a ring counter. Again, we can all again decrease this part of the code. We can again optimize it. How we can do that? 3 colon 1. Q3, Q2, Q1, those all the 3 digits are included in this 3 colon 1. We can do that as well. If we run it, this is the most optimized part of the code. Okay, now we generate functional simulation netlist and we run it, we execute it. Oh, sorry. We simulate it and we can see, and this is again correct, 1011, 1101, 1110. So you can see these 4 lines can be replaced by a single line and the code still works and the code becomes more efficient. So that's all for your Verilog class. We will not be having any more Verilog experiments. Your homeworks of the Verilog task will be given in box. If you have any confusion, you always feel free to put your comments in the discussion box, and I will try to solve those problems, and I'll try to solve any issues that you have. And we'll be having live class, and in the live class also, if you have any problem, you can discuss, and I'll be trying to solve those problems. Thank you so much. That's all for your lab class. Thank you.